Okay, so we are looking at a practice problem from the unit on rotation. We're going to be looking at 33.1 here. And these practice problems are all practice problems on conservation of some angular momentum. That's what we're conserving here, angular momentum. We're essentially going to be using this idea that an angular momentum, or a moment of inertia multiplied by some angular velocity initially, equals the final quantities of these. And this is very similar to our old idea where initial momentums equal the final momentum. Now what we have in this problem is we have a 1.6 kilogram disk with a radius of 0.63 meters. And it's rotating freely at 55 radians per second. So we've got a nice omega right here. And then this mass and radius together, that's going to help us find our moment of inertia I. And they're rotating around an axis perpendicular to the center. So what this means here is that we have we've got a disk like this, and the axis is going through the center of it. A second disk that is not rotating is dropped onto the first disk so that their centers align and stick together. So we take a second disk here, and we drop it on it so that they've stuck together. Okay? We know the mass of the second disk and the second disk's radius. What we'd like to know now is what is the angular velocity of the two disks when they combine. So we are using a conservation of angular momentum here. We are using this idea. And one of the features we'll have to use about this is because these two disks are sticking together, one is falling onto the next and then they're bound, our final moment of inertia is going to change. And one thing that we saw in a prior video, and what we'll have to remember, is that when we take two objects and we rotate them about the same axis, we can just take their individual moments of inertia and add them together. So we can just take whatever the first disk is plus whatever the second disk is, add them together. That's our final moment of inertia. Okay? If we forget our moments of inertia, we're going to have to go to our best friend, because on our backside at the very bottom of this, there are all the moments of inertias that we'll need here. In our case, we are operating with solid cylinders, so our moments of inertia of each of these individually is going to be a 1/2 mr squared. So setting this up, for our initials, the initial moment of inertia as a cylinder for just this bottom piece here, that's a 1/2 mr squared. So 1/2 times the mass of that initial disk, which is 1.6 kilograms, times the radius of that disk out from the edge, or from its axis of rotation, which we know is just the radius of it. So that's just 0.63 meters, and don't forget that square. We multiply that by the initial angular velocity, that's that 55 radians per second. So there's our 55 rads per second. And then this has to equal the final moment of inertia multiplied by some final angular velocity. And that final angular velocity, that's what we're actually looking for. So what is this final moment of inertia? Well, it's just the moment of inertia of both disks added together. The first disk's moment of inertia, and I'm going to put this in like a very large bracket because I want to make sure that I add these moments together first. The first moment of inertia that I have is that 1/2 times 1.6 times 0.63 squared. That's the same thing we had on the left side. But we need to add to that quantity the moment of the inertia of the second disk collapsing to the top, which had a mass of 0.45 kilograms and a radius of 0.38. So close out your parentheses. So that's going to be 1/2, because that's our coefficient in front, times the mass of 0.45 multiplied by a radius here of 0.38 meters, and then square it. And this entire quantity here, that is our final moment of inertia. Okay? And then we are just multiplying this by our final angular velocity, and that's what we're looking for. So if we look at this here, we've got a lot of numbers, but only one variable we're trying to find, that final angular velocity. So at this point in the problem, all of the physics is done. We just are stuck calculating with the calculator. And we always want to make sure that whenever we use our calculators, we be as careful as possible. Oftentimes, this is where we'll make mistakes when looking at numbers. We've done all the physics right. Let's not let calculators mess up our good answers. So when doing this, I like to try to collapse things down individually first. I'll take 0.5 or 1/2 times 1.6, and then I'll multiply that by the quantity 0.63 squared. So I'm making sure I square just the 0.63. When I do that, I get, for just this, 0.31, I will just round that up to 8. This is helpful because this same quantity comes back over here. So I don't have to do that again. Now I'll multiply that by the 55 radians per second, and this gives me, for everything out here, a 17.46. Now on the right side, I'm going to take the 0.318 that I had from this first term, and I'm going to add that to whatever I have from the second disk's moment of inertia here in blue. So what I'll actually do is I'll use the blue quantities. I'll put those into my calculator. So 0.38 squared times 0.45 divided by 2. I get 0.0324, or 0.325 if you want to round, whatever. I'm going to add 0.318 to that. When I do that, I am going to find I have 0.35 multiplied by omega f. Now this is very straightforward. I can simply divide by 0.35, divide by 0.35. This will give me a final angular speed of 49.88 or 49.89. And our units here are going to be radians per second. I know they have to be radians per second because I'm looking at an angular speed. I didn't really carry my units very much through this problem because my units here are going to become like a little annoying. I'm going to have meters squared and kilograms and radians per second. I could carry them through and make sure we got the right answer, but trusting my mathematics and knowing what angular speeds need to be at the end, radians per second, that's what we'll find there. Okay? So with that, this problem here is finished, a first little conservation of angular momentum. We'll be doing 2 more in our following videos, but until then, adios, and take it easy.